Welcome back to another tutorial for Unit 3 in the General Engineering syllabus, looking at the Queensland curriculum. And today we're going to look at shear force and bending moments. First of all, we're going to unpack what shear force and bending moments are talking about, and then we're going to unpack each of them individually, showing you how to solve the problems and draw the diagrams. Okay, so first of all, you might hear this term called bending stress. Now, all we're really talking about is what are the stresses occurring on a member when a bending action occurs on that member. So if you look at the diagrams there, we've got a piece of balsa wood that's flat compared to when we apply a load to that balsa wood in the middle and it creates a bend in it. There's now stresses in that member. So that's really all that bending stress is referring to. Okay, next up is the idea of bending moments. Now, one of the things that I want you to really focus in here is the words that are used. Bending, we've just talked about bending, and the second word that's used is moments. And moments is something that was explored in Unit 1. Okay, so you might need to revisit moments if you are a little bit rusty on that sort of stuff. But essentially, I want you to think about here what it is that we have got. So in this particular example, we've got two students sitting on a beam, and I've gone and worked out that Tom has a mass of 60 kilograms, Jake has a mass of 80 kilograms. The length of the beam is 1.8, and they're both sitting an equal distance apart. I've then gone and worked out what their total weight is in newtons, which is seen there. Now, really, what we've got here is a beam that they're sitting on that's positioned like that. And what we're trying to gain an understanding of is what happens with the stresses in that beam when they sit on it. So the beam is going to go from that sort of flat, straight position to something like that that represents the bend. And what we're really trying to do by solving these problems is understand what that bend looks like accurately and how we represent that in a diagram. If we were to draw a free body diagram, the diagram is going to look a little bit like that. Try not to get too hung up on where I've positioned the blue arrows. I know that they're not right in the student centers, but I've sort of done that deliberately just to make the example a little bit easier to work through. Okay, shear force. Now, shear force and bending moments are related to each other, and quite often you will see that they are talked about together, and you might be asked to solve a problem where you're asked to do bending moments and shear force diagrams together. They relate to each other, but they are a little bit different. What shear force is talking about is when we've got forces acting on the member, just like our diagram suggested, and we've got our reactions, right and left, you then hopefully start to gain a little bit of an understanding of that Isaac Newton's third law. For every action, there is an equal and opposite reaction. So when we've got a force pointing up and we've got a force pointing down, and notice that those actions are sort of slightly offset from each other. So we need to sort of ask ourselves what's occurring in this space here, okay? And really this is what's happening. We don't actually see the beam shear in half like that, but that's really what the forces are doing to the beam, okay? So we've got that reaction left, which is pushing up, and we've got force 1, and in between that space, we've got our shear force. But we also have a shear force that's occurring here between the two forces, and we also have a shear force that's occurring here between force 2 and the reaction right. And we can label those as shear force 1, shear force 2, and shear force 3. So now we're going to get into looking at how we go about solving those problems. Okay, first the reactions. Now I'm going to go through this with you, but I'm not going to go through it really, really finely. If you need a refresher on reactions, go and check out my video on reactions to brush up on that. Okay, this should be fairly simple for you to do if you're well versed in this. So as I showed you before, we already have what the student's mass is talking about it in terms of their weight in newtons, and those are listed there. We've drawn our free body diagram, and I'm going to start by taking my the sum of moments from the left, okay, and remember that that is solving the reaction on the right. Okay, so we've got the force 1 multiplied by the perpendicular distance, okay, minus force 2 multiplied by the perpendicular distance back to the left, okay. We're then adding the reaction right, which is assuming an upward force multiplied by the total distance of the beam, and we're finding that our reaction right is then 730.3 newtons. So therefore, if keeping in mind Newton's third law, if we've got sum of moments in the vertical equals 0, okay, because anything that's going down needs to be equaled out by anything going up, okay. So we then solved our reaction left as well, and we can see that those reactions are different because the mass of the students is also different. Okay, so there's all our data now that we need to start solving our bending moment diagram. Okay, sorry, our shear force diagram we're looking at now. All right, so the first step here is you need to start breaking up your system into each of the shear force components, okay? And this is how we represent that. So we've got our shear force 1, our reaction 1 acting in an upwards direction, and that's labeled, okay? And then we move across to that position of our shear force 1 acting down, all right? And that is our shear force 1. And if we've got shear force 1 equals sum of forces, we've only got one force in play, so therefore our shear force 1 is 643.1 newtons, and it is a positive shear force acting up. Okay, so shear force 2 is going to look like this. Again, we're working from the left here. Now this is a bit of a convention thing. The convention is that we work from the left, we move across towards the right, and I'm not 100% sure why, but we don't actually include the far right reaction in our shear force diagrams. Okay, so with our second shear force, we've got our reaction from the left, 643.1. We've shifted across now, and we've got our force 1 going down 588.6, and we've then moved across to the midpoint between our next two our two forces going down, and that there gives our second shear force 2. So again, shear force 2 is going to be the sum of forces. We've got a force going up in the positive, we've got a force going down in the negative, so we just take those two away, and that leaves us with 54.5 newtons, and again, that is a positive force going up. Positive answer means it's pushing up. Looking at our last shear force, we've worked our way along now. This is the third shear force in the system. Again, we've got our force going up as our reaction left, 643.1. We've now got a force acting down, 588.6. We've got another force acting down, 784.8. So I want you to ask yourself here, if we're just doing addition of forces, and really guys, this is no more complicated than addition and subtraction. Do you think we're going to have a positive or a negative result here? Okay, and of course, when we go and do the maths on it, shear force 3 equals again sum of forces. We take all of those away, and we end up with a negative shear force this time of negative 730.3. Now this is, of course, a negative shear force. Okay. A point to note: positives and negatives don't really exist in this case in a shear force. What the positives and negatives is really relating to is more so about the direction whether the force is moving up or the force is moving down. Okay, so that's just a little bit of a side note, but it's useful for us to include the positives and negatives for us to get a better grasp on all of that. All right, so we've got all of our information now. Now we need to be able to draw what we call a shear force diagram. All right, so the first thing I want you to do with your shear force diagram is always go and draw your free body diagram up the top. Now it's best if this is done to scale. All right. Now, all I mean by that is if we've got 0.5 of a meter from each of the ends of our system, I don't know how you want to draw that. You might, if you've got enough room on your paper to draw the 1.8 meters as 180 millimeters, you can, and then the 0.5 of a meter would end up being 50 millimeters. However you want to work your scale, but it's really helpful if you get it in scale. So we've got our free body diagram, and the first thing we're going to do is work our way down. Now you need to make sure you've given yourself enough space. So you're going to have to sort of think a little bit ahead what sort of scale you're going to use, which you'll understand a little bit more in a sec. Now this horizontal line that I've drawn represents our shear force 0. Okay, so that's our base starting point. We're then going to project lines down from all of our forces. So notice that I've projected down from my reactions, and I've also projected down from those negative forces acting on the beam. We're then going to create a scale. Now, in this case, I've created a scale that represents each line as 50 newtons. We're going above the line, and we're also going below the line. Okay. Now this part is really, really simple once you understand. You take the information that we worked out before and you go and just draw across. So that first one that we found was 643.1. I've just removed that scale behind just to make it a little bit clearer for us to see. The second shear force was 54.5 newtons. It's above the line. It's a positive force. And the third force was 730.3 newtons, and it was a negative force going below the line. Okay, that's really our shear force diagram. It seems to be as well convention to generally always hatch your boxes and include the magnitude of the shear force in the box as I've done there. There we have it, our shear force diagram. Alrighty, typically we would also, you would often be asked to draw a bending moment diagram when you're asked to do the same thing. So again, here's our free body diagram with all of our information on it. We're going to work out our bending moments. Now I said at the start of this video that you want to think about that term moments. Okay, remember moment is a turning force. Okay, so we've got a pivot point and a turning action that's occurring. All right, so in this case, we're looking to our first moment. Okay, and that's our bending moment there, occurring there at that first position. We've got bending moment 1 equals sum of moments. So this one's nice and easy for us. Okay, again, similar to our shear force, we're working from the left to the right. All right, so this one should be nice and easy. And again, we are in Newton meters. Okay, so make sure you're using the correct units as you go. Bending moment 2 is going to look like this. Now, a couple of things here. The perpendicular distance that we use to solve our bending moment is actually going to be taken from where the bending's occurring. It doesn't come from that far left side as it typically does when we're solving reactions, for example. Okay, so that's something that you might get tripped up on if you're not careful. So for our second bending moment, it then looks like this. Sum of moments equals 643.1 newtons multiplied by 1.3, because that's our total distance, minus 588.6, and this one is multiplied by 0.8 meters. Okay, punch that into your calculator, and that gives you your result. So we've just got the two bending moments that's occurring here. We've got our free body diagram, and just like we did with our shear force diagram, we can then start by projecting our lines. So we project our lines down exactly the same way that we did with our shear force diagram. Just like we did with our shear force diagram, we can then put in our zero line, okay, our bending moment zero. Now, this is a little bit weird to think about. We're going to draw in our scale. All the numbers that we came ended up being positive numbers, which are going to indicate that we're moving above our line. Okay, that's correct, even though you can probably imagine that the bending force is going to be pushing the beam down. Okay, so for whatever reason, the diagram, even though the bending force is pushing the diagram down like the beam down like this, the bending force, the bending moment diagram is going to actually be sort of inverted on that, and it's going to look like a mountaintop. So don't get confused with that one either. So we've got our zero baseline. We've now got our lines for our scale. We've put our values in. So I'm using the same scale that I used before. And then it's just a matter of plotting our points. So we had two bending moments, and I draw my lines across. Now this is really important that you do this to scale so that it's accurate. We've then got our two positions, and those two positions are going to be in line with where our forces are, 321.55 Newton meters and 365.15 Newton meters. We then just play dot to dot, nice and simple, and there we have our bending moment diagram. Always good practice to put the magnitude of the bending moments on there. Make sure that your bending moments return back to the reaction supports, back to that zero position. And as we did with the shear force diagram, remember to hatch it as well. There we have shear force and bending moments.